On this episode of Nova Science Now. No, it's not moving day at the planetarium.
Telescope number 7.
These new telescopes are searching for the cosmic holy grail. Alien planets that can support life.
We want to find Earths. We want to know whether we're alone.
Can this ambitious astronomer, working with simple equipment,
No matter how high-tech the operation is, never leave home without duct tape.
and dealing with unexpected guests,
Those appear to be paw prints.
Paw prints?
be one of the first to find a new world where life could exist?
If you find one habitable planet, that's a huge discovery.
And one of these two paintings is a Van Gogh original worth millions. The other, a fake, created by this artist for a Nova Science Now computer challenge.
Do you think she has a shot against the computers?
I think it will be a challenge. Yeah.
3 teams of computer scientists
This white thing is showing through.
come up with programs to pick out our fake among 5 Van Gogh originals.
These are genuine Van Goghs.
Will this new technology work? The results may surprise you as much as they did us. Also, in this episode's profile, you'll meet a biologist studying some spiders whose mating habits are to die for.
She'll actually pierce him and eat him while he's mating with her.
Why would any creature behave this way?
It's what evolution's all about, right? It's sex and it's death, and it's all wrapped up into one really interesting story.
All that on this episode of Nova Science Now. Hi, I'm Neil deGrasse Tyson, your host for Nova Science Now. Wouldn't it be cool if the universe were like it is in a lot of movies? Filled with aliens, even intelligent life that we could meet, socialize with. Hey, mind passing the nuts? But if there are other creatures out there, where would they be? We've been searching the skies for a while now to find planets other living things could call home. And now planet hunters say they're tantalizingly close to that goal. Not nuts.
Most of us, when we're children, we look up into the night sky and we wonder, what is our place in the universe? Are we somehow related to the stars, the planets? Are there other beings out there? The Holy Grail, for me and for all of the astronomers working in my field, is to find an Earth-like planet, and especially a habitable Earth-like planet.
Jeff Marcy has spent his career hunting for other worlds. But it's clear that not every world is friendly to life as we know it.
What renders a planet indeed suitable for life? Well, clearly you want a planet that has some water on it, because water is the cocktail mixer that allows the chemistry of our bodies to even work.
If we want a planet with liquid water, then it can't be too close to its star. That would make it too hot, and the water would boil away. And it shouldn't be too far away either. Too cold, and you'll likely get an ice ball. What everybody really wants to find is a little rocky planet whose distance from its star is just right. A Goldilocks planet with oceans of liquid water. But hunting down a planet just like ours has been a daunting task. In fact, not long ago, we hadn't found any planets beyond our solar system. None at all. They're so far away and so dim, they get lost in the glare of their own suns, the stars they orbit.
It's like a lighthouse and having a tiny firefly next to the beam of this lighthouse. This is what you're looking for.
So to improve their chances, most planet hunters, like Jeff Marcy, focus on stars.
Here we go, first star, shooting. Wow, that's beautiful.
Readout complete.
Okay, we can go to the next star.
Using the big, powerful Keck telescope in Hawaii, Jeff looks for slight wobbles in the star's position, signs that a planet might be orbiting.
These planets do one thing that is just glorious. They're so massive that as they orbit the star, they pull gravitationally on the star. So if you just watch the star, you see it move to and fro.
This so-called wobble method of planet hunting is a little bit like watching people walk their dogs.
You watch the dog owner, never mind the dog itself, and the dog owner gets kind of yanked around as the dog goes to and fro.
The idea is you don't have to see the dog itself to know that I'm getting yanked on by something.
And of course, that's what we do. We watch stars that are being yanked on by their host planets. And of course, in that case, the leash is gravity.
Thanks to the wobble method, Jeff and other hunters have so far tracked down hundreds of planets. Most of them are enormous balls of gas, like our Jupiter, which itself has 300 times the mass of Earth. And some orbit extremely close to their stars.
They're so close, skimming along the surface of the host star, that these planets are blowtorched to 1,000, 1,500 degrees. So they're so hot that the organic molecules of which our bodies and other life forms on the Earth are made would disintegrate.
It turns out, if we want to find more comfortable Goldilocks planets like Earth, there's a little problem with the wobble method.
Okay.
If a hot Jupiter is like a big dog yanking on its owner, then Earth is kind of like this. It might be full of life and totally lovable, sure, but gravity-wise, it's kind of wimpy. It's just not going to have much of an influence. If you're only watching me, you might never know the dog was there. Same goes for a star out in the galaxy. The teeny tiny wobble caused by an orbiting Earth is really hard to detect. And that's why, despite all their successes,
So far, we astronomers haven't found a single Earth, not one.
if we want to find a place for life, we might need another method. Recently, I headed up to Mount Hopkins in Arizona to meet another planet hunter. One who's using an entirely different approach in the search for habitable worlds. Dave Charbonneau's experiment is based in an old shed.
So this is the Mirth building.
Once used to track Soviet satellites during the Cold War.
We'll slide back on these rails.
As planet hunting projects go, this one is relatively low budget. Because unlike the wobble hunters, he doesn't need the biggest, most powerful telescopes.
You know, when I walk into big observatories, I expect big telescopes. These look kind of puny to me.
But there are lots of them.
Dave can use smaller, cheaper telescopes because in his search for habitable worlds, he's not looking for a wobble at all.
It may be easier, instead of looking for the wobble, to actually look for an eclipse.
We can see this kind of eclipse or transit right here in our own solar system when Venus or Mercury passes between Earth and the Sun. But when the planet and its star are light years away, you can't see a round silhouette, but the star will appear to dim ever so slightly.
And so the idea is as the planet passes around in front of the star, then it'll block some small part of the light, and so we'll measure this little miniature eclipse. Essentially, we'll measure that the star will get fainter for a short period of time.
These kinds of transits are pretty rare, so Dave is casting as wide a net as he can, tracking a couple of thousand stars. That's why he needs a lot of telescopes.
Here's the mirror. It's good.
All right.
Today, Dave and his team recruited me to help set up a few more.
Telescope number 7.
This is number 7. First thing we need is the mount.
Let's do it. No matter how high-tech the operation is, never leave home without duct tape.
Well, this is the power cable,
Power cable.
and this is the data cable. Power goes in, planets come out. Just to make sure that nothing gets...
Using this new transit method, Dave has already discovered several new planets. But so far, they're all the size of Jupiter or bigger, and not habitable.
list of 2,000 stars that we want.
Now, he's hoping to improve his chances of finding a small Goldilocks planet by focusing his telescope on a particular kind of star called a red dwarf. Red dwarfs are much, much smaller and dimmer than our sun. So if a small planet passes in front of a red dwarf, it will block out a larger percentage of its light than if it had crossed in front of a bigger star like our sun. As sundown approaches, the roof of the shed slides away. And when the stars appear, the telescopes go to work, swooping around to point at one red dwarf and then another, hunting for any trace of a transiting planet. The telescopes are designed to do their job alone on the mountaintop. But I saw evidence that they might have some visitors.
Well, wait, stop. There's smudges on this mirror.
Yeah, unfortunately those appear to be paw prints.
Paw prints?
Yeah, we've come to realize recently that it appears that some animal is coming in here, perhaps during the night, and maybe looking at itself in the mirrors.
Dave hasn't discovered the culprits yet, but whoever they are, they haven't stopped the telescopes from gathering thousands of images of stars. As the pictures come in, a computer immediately analyzes them, looking for the slightest dimming.
The one right in the middle. Right.
But the telescopes will see it only if the planet's orbit is aligned just right, so that it passes between us and the red dwarf star.
So you need star systems that are edge-on to our view.
Right.
And you don't know that yet about your 2,000 stars.
That's right.
It sounds like it's a challenge.
That's right. We are looking for the needle in the haystack, but if you find one habitable planet, that's a huge discovery. That's worth it. That justifies all of this.
Okay.
Dave has high hopes that the transit method is a great way to find habitable worlds. And he's not alone. After years of preparation, NASA just recently launched the Kepler Space Telescope. Over the next 3 or 4 years, Kepler will be looking towards the constellation Cygnus, keeping watch on more than 100,000 sun-like stars, searching for transiting planets. Since it's high above Earth's blurry atmosphere, Kepler has the ability to find a planet pretty much like our own, orbiting a star just like our sun.
We want to find Earths. We want to know whether we're alone. And Kepler is the first mission that can find true twins of our Earth. Earth-mass planets, Earth-sized planets that orbit in an Earth-like distance.
Of course, if and when we locate a livable planet, we'll want to know, is anybody home?
They're alive.
And when I say anybody, I don't necessarily mean one of these movie guys. I'd be thrilled at signs of microbes. As we sniff out the chemistry of life on distant worlds, eventually we should answer that question too. And the cool thing is, pretty soon, we'll know just where to look.
We are just at the verge of finding these planets. We can answer a question that was asked thousands of years ago. Maybe in 5 years, maybe in 10, but we'll answer it.
We should know within our lifetimes whether there are other Earths and whether some or most of them are habitable, like our own Earth. What a lucky time to be alive.
How do you identify a true masterpiece? We don't usually think of a great painting as something that can be reduced to numbers.
Got a couple more threes right over here.
But a few scientists might disagree. They say that if you take away the color and break down a painting brushstroke by brushstroke, you'll find a complex pattern of numbers. A pattern unique to every artist. And, as correspondent Chad Cohen reports, it could provide a crucial clue if you're trying to tell the real thing from a clever forgery.
Deep in the storage vault of the Van Gogh Museum in Amsterdam, a precious canvas is being photographed. The Reaper, painted by Vincent van Gogh in 1889, has the thickly layered paint and bold curves the artist is so famous for. But are we looking at the real thing? Because there are two Reapers in this vault. One, as you might expect, worth millions. The other, a copy, worth no more than the oil and canvas it was painted with. Can you tell the difference? It's something hundreds of collectors ask the Van Gogh Museum to do every year, convinced they own a masterpiece by the great artist.
We get many questions for expertise here. Our opinion is asked all the time. And there are many fakes that have been around for decades. But it's a problem for any renowned artist because money, of course, is very tempting.
This is serious money. $50, $70, $80 million a piece for some of the best-known paintings. Even the Van Gogh Museum was fooled into buying a fake back in the 1970s. It's a 19th century painting called View of the Eye, Amsterdam's Inner Harbor. It wasn't originally intended as a fake. But years later, someone forged Van Gogh's signature onto the canvas. So how do you determine if a painting is the real thing? In May of 2007, the Van Gogh Museum explored one of the latest scientific methods of art analysis by hosting the first international workshop on computer image processing.
These images are represented in terms of numbers.
Eric Postma directed the technical presentation.
The purpose of the project was to look at these paintings and try to determine if we could distinguish between real and fake Van Goghs.
The computer scientists focused on one of the most revealing traits of Van Gogh's work. As the museum's head conservator, Ella Hendricks, showed us, it's the way he applied paint to his canvas.
I would tend to really want to get close and look at these, for example, these very nice white strokes in the foreground that were added at a late stage. And if you look very close, you can see these sort of trailing drips of paint as he literally scooped up the paint from the canvas, lifting his brush and then carrying the trail of paint.
It turns out that Van Gogh's brushstrokes are crucial markers not only for critics and connoisseurs, but for computers as well.
The pattern of brushstrokes is very specific and very indicative of a painter. So the first selection that you make when you start to analyze these paintings digitally is to select the level of individual brushstrokes.
The computer scientists create programs which examine a painting from different angles to determine the direction of each brushstroke. Collecting the brushstroke patterns from more than 100 paintings establishes a baseline for Van Gogh's style. But could the computer be fooled? Could an artist specially trained to copy the old masters duplicate Van Gogh's style? To find out, we commissioned Charlotte Kaspers to carefully imitate every detail of Van Gogh's brushstrokes. She's an expert in art reconstruction, using historical materials to copy famous paintings so museums can decide how to preserve the originals.
The best would have been to sit next to the painting, but, well, that was just not possible.
The Van Gogh Museum doesn't allow artists to paint in front of the originals, so she made her own photos of the Reaper.
I couldn't bring the painting home, so I had to take a picture, and when it's a digital one, you can blow it up on your computer, so that was what I did.
Knowing that the scientists would be focused on the pattern of Van Gogh's brushstrokes, Charlotte's job was to perfectly match his technique.
I had a picture next to my canvas I was painting on, and I could blow that up so I could have a close look at the paint surface of the original painting from a picture.
How do you think that trying to be him ultimately influenced the painting itself?
It's less spontaneous. I was just switching all the time my eyes from my canvas to the picture and trying to do what he did.
We had a young artist copy one of the master's paintings. Did you get to see the
I did get to see it, yeah.
What did you think?
I think she did a remarkable job because she's made a very accurate copy of the rhythm of the brushstrokes, but managed to do it in a spontaneous way.
So do you think she has a shot against the computers?
I think it will be a challenge, yeah.
The challenge begins by turning Charlotta's copy of the Reaper into a color photograph, which is then turned into a high-resolution black and white scan. Identified only by catalog number, it takes its place beside 5 real Van Gogh paintings, creating Nova ScienceNow's test for 3 computer teams: Penn State University, Princeton University, and Maastricht University. Eric Postma leads the Maastricht team.
So here's a famous Van Gogh.
Yeah.
Van Gogh.
Van Gogh.
Van Gogh.
Van Gogh.
Van Gogh. The sower.
De zaaier.
However you want to say it. How do you begin? So you look at this, it's a beautiful painting, but you're going to strip it of its beauty, one layer of its beauty right now.
Yeah, in fact we do, because we translate the entire painting into numbers.
Postma's software scans the whole painting, identifying areas of contrast. The more contrast, like the dark tree branch against the light sky, the larger the number assigned by the computer. If the contrast is less extreme, like the edge of the sun against the sky, the number is smaller. When all the contrast patterns are combined, a statistical portrait of Van Gogh's style is created.
Well, these are genuine Van Goghs, and this is a known fake. The faker tried too hard to mimic Van Gogh.
And by trying too hard, that means
too
painting
much.
too much.
Too much, exactly.
I see.
Someone copying Van Gogh paints too many brushstrokes to get it right, and the computer identifies them as areas of higher contrast. First, the program analyzes the brushstrokes from 6 different angles, then combines them to reveal areas where they overlap. More overlapping brushstrokes show up as brighter areas. Fewer overlaps are dark. Look at this famous painting Van Gogh did of his bedroom. As the computer separates out each angle, it highlights the brushstrokes painted in that direction. Putting them all together reveals a brushstroke map of the painting. Now look at the forgery. The computer identifies more overlapping brushstrokes in every direction, 10 times as many as the Van Gogh bedroom. The genuine Van Gogh paintings display fewer brushstrokes than the forgery.
If you deliberately try to mimic Van Gogh, then it's not natural anymore, and then you tend to overdo it. And this overdoing it results in high numbers, and that could be one way of detecting a fake.
I'd like to see what the zoom-in gives there.
Ingrid Dopschi and the Princeton team have also been looking at the 6 paintings in our test, searching for the fake.
Okay, so...
If you try to make a copy, you would pay so much attention to what you're doing that you probably paint it more slowly and with a more restrained hand than Van Gogh himself would have painted, and we expect that to transfer as well.
For James Wang and Jia Li from Penn State University, Charlotta's copy seemed to blend in with the other 5 paintings.
Just by looking at the pictures, they all look very Van Gogh. So that's why later we also tried a statistical modeling approach.
So you get a kind of segmentation of the paintings.
All the science teams had less than a week to distinguish the fake from the real Van Goghs.
Typical brushstrokes.
I think we see more contrast in the grooves than in the ridges.
Oh yeah.
This white thing is showing through.
Oh, yeah.
Would they pick the sunflowers, the sower, any of the other 3 genuine Van Goghs? Or would any of their computer programs successfully choose Charlotta's version of the Reaper? The analysis is finished, and it's time to take her painting to the Van Gogh Museum, where the scientists are waiting.
Okay, the moment of truth. Do you all have an answer?
Yes.
Yes.
We're ready to bring in the artist?
Yes.
Okay, Charlotta, This is Charlotte Casper. She painted the painting that you guys tested.
Oh, very, very nice to meet you.
Do you want to come on over and reveal it? Well, bring it on over. Don't open it yet. Bring it on over, Charlotte. All right, so what do y'all got?
687.
687. Right.
687. The one.
You guys match. That's 2 for 687?
And that's 3 for 687.
Yeah. All right, that's your final answer. You're sticking with it.
Yes, yes.
Yes.
Here we go.
All right, Charlotte, let's see.
Okay, yes,
let's
yes,
see.
yes, yes.
Wow.
Oh, yes,
687, The Reaper.
yes. Got it.
So how long did it take for you to finish the painting?
I worked 2 days on this one.
How long did it take you to analyze the painting?
Oh, we took 2 days too.
In fact, Van Gogh himself completed many of his most famous paintings in 2 days or less. And they've kept art collectors and experts busy for more than a century. They're not there yet, but computers will ultimately speed the process along.
The most valuable thing about these techniques is that they can help art experts. You just can scan over the entire painting, and they do it in a completely unbiased way. And that's the great advantage of computers.
Nature is full of strange behavior and displays, much of it done in the name of love. Take the peacock, for example. Look at this thing. How can you even walk with all of that weighing you down? And it's just to attract a lady friend. And how about the anglerfish? The little male latches onto the female and doesn't let go, ever. In this episode's profile, we meet a biologist whose subjects engage in some of the weirdest, even gruesome behavior. She insists it's worthwhile because it passes their genes onto a new generation.
I do really like horror movies. Really entertaining to watch horror movies that make spiders into villains. They capture something essential about what it is about spiders that scares so many people. The intelligent, stalking nature of the way that they go after their prey, maybe how fast they can move. The spiders stalk their prey like cats, you know, they're quiet. You would turn around and suddenly one of them's there.
Meet Mediane Andrade, evolutionary biologist at the University of Toronto. Although she loves a good scary movie, Mediane isn't really afraid of spiders. In fact, she's the leading expert on the Australian redback, a poisonous spider and a close relative to the black widow, with one of the strangest mating behaviors in nature. The tiny male will climb onto the much larger female and actually offer himself up as a meal.
He will insert in the female, and then he'll flip and basically do a somersault to a position where his body's immediately above her fangs.
As they mate, the female will begin eating the male alive.
She'll actually pierce him and begin to chew up parts of his abdomen and eat him while he's mating with her.
Studying the mating habits of potentially deadly spiders is not for the faint of heart. But there was a time growing up in British Columbia when Mediane herself was a little squeamish.
I remember in particular one day when My brothers and I were watching TV, and this little spider sort of crawled across the floor, and we all just lost it. And we put a bowl over top of it and decided that I was going to quickly lift up the bowl, and my brothers had the vacuum. And of course, for a joke, the brother who was supposed to turn it on didn't. So there I was with the bowl up, and the spider starting to freak out. And, you know, it was one of the traumatic moments of my childhood. Things have kind of changed since then.
So how was a girl who was once terrified of simple house spiders inspired to go on to study these eight-legged creatures? As a graduate student, she became intrigued by a strange phenomenon found in the insect world: sexual cannibalism.
The classic systems in which everybody from school kids to naturalists often find out about sexual cannibalism are praying mantids and the black widow spider.
In the case of the praying mantis, the females often eat the males during the mating act. As her research subject, Mei-Dian selected the Australian redback, a spider whose females were rumored to possess a big appetite for their mates.
I got some of the spiders in the lab and waited and waited and waited, and nothing ever happened. And then finally I realized, well, you know what? They're nocturnal. They're active at night. So I have to start coming in at night. And again, I waited and waited, and not much happened. And so one day I just said, you know what? I'm staying all night. It's got to be happening somehow. And so finally, at about 2 or 3 in the morning, after a 5 to 8 hour courtship, I finally saw it. I finally saw this behavior I'd read about and that I wanted to base my research on.
What she saw was the male spider literally throwing himself into the jaws of the female as they mated.
I mean, it was amazing. It was like a eureka moment, and I went running all over the building, and of course no one was there because it was the middle of the night, and I finally, I think, found a custodian and you know, told him about it, and he thought it was pretty strange, but still it was a fantastic moment.
Now, Mei-Dian's true test would begin. She left her home in Toronto for Australia, where night after night she searched for poisonous spiders.
It was a very solitary, slightly creepy kind of a thing. Sometimes it would harken back to those horror movies because I would be mesmerized in what I was watching on those webs, and then I'd suddenly realize I'm in this area all by myself. It's 2 in the morning. It's pitch black. Is that a noise I heard over in the bush?
And at all times, she had to remember that these spiders were potentially deadly.
The venom goes into your bloodstream and your lymph system, and it causes pain, sweating, muscle contractions, vomiting, diarrhea, fever, chills.
But the risk would be worth it if she could answer this evolutionary riddle. Why would the male spiders sacrifice themselves? There had to be some benefit for the species.
My fieldwork was aimed at asking about male opportunities for mating in nature. Was it true that males often only got one chance at mating or only encountered one female in their lifetime?
She meticulously tracked and documented the lives of nearly 2,000 male spiders. And in the end, the results were astonishing.
Unfortunately for male redbacks, they're fairly small. And once they're off their web, they're actually really vulnerable to all sorts of other animals. So most males are killed one way or the other before they reach a female.
In fact, Mei-Dian showed that only 1 in 5 male redbacks ever got to mate at all. And when they did, their ultimate sacrifice paid off. The male spiders who somersaulted into the jaws of the female during the mating act produced more offspring.
For redbacks, if a female eats the male, she actually lets him mate for longer, and that means that he transfers more sperm and he'll have more babies.
This explains how the redback spider's bizarre mating behavior evolved.
A male who throws himself into the jaws of death and has 1,000 more offspring than his competitors, that trait is going to go on into the next generation. So the next generation, we're going to have 1,000 more males who do the same thing. And presumably that's what happened in the evolutionary past in redback spiders.
She published her discovery as solo author in the prestigious journal Science, a rare feat for an established scientist, much less a master's student.
I mean, I almost cried. I was just so floored by the fact that other people thought it was important too. It was fantastic.
Mei-Dian went on to get her PhD, and today continues her research on the Australian redback. And she now has a mate of her own, fellow professor and arachnid expert Andrew Mason.
I first met Mediane at the lab where I was working doing my PhD. And I looked up from my work and sort of briefly explained what I was doing, and she asked a question about it, and that was it.
We looked up, and I mean, I could almost say that that was it from the moment we saw each other. I never used to believe in that stuff, but I do now.
They even spent their honeymoon hunting for bugs in the Canadian Rockies.
It's worked out better than I could have imagined. Certainly better than my parents would have imagined when I told them I wanted to study spiders, probably. I'm guessing they're expecting an old maid.
And together, Mediane and her husband are continuing their work on sexual cannibalism, with the hopes of making further discoveries about the secrets of evolution.
A lot of people will come up to me and say, why sexual cannibalism? Why would I study something so strange for so long? But really, in a way, it's what evolution's all about. It's sex and it's death. And it's all wrapped up into one really interesting story.
The human brain is awesomely complex and difficult to understand. But researchers are now unraveling the secrets of how our brain forms and develops, from the time we're a small embryo up through adulthood. And that's crucial, because not only does it help us understand who we are, but it'll help us treat and possibly even cure some of the most frustrating diseases, like autism. Correspondent Chad Cohen met the researchers who are finally uncovering clues to what might cause this devastating disease that up till now has been a mystery.
This is what most people picture when they think of autism. Dustin Hoffman in the movie Rain Man.
Hey, man.
He's obsessive.
Of course, it's 27 minutes at Jeopardy. Practically 26 minutes at Jeopardy.
I got my boxer shorts at Kmart, Cincinnati.
What did I say, Ray?
He's repetitive.
What I tell you, Ray, we are not going to Cincinnati, and that's final.
I got my boxer shorts at Kmart.
Raymond, that is final. Did you hear me?
I want to be short.
He's lost in his own world. In real life, autism is a devastating disorder that seems to be on the rise. It has a wide spectrum of symptoms, and clues to what causes them are few and far between. One thing we do know is that it runs in families. These twins, Maya and Evan, both have it, as do brothers Colin and Liam.
Wow, you're doing this so fast.
This boy Jeffrey is autistic, and so is his brother Zachary. In fact, when one child in a family has autism, the odds that siblings will have it skyrocket from about 1 in 150 to 1 in 5. This suggests a genetic cause, but so far, autism genes have been elusive. Now, scientists are embarking on the biggest hunt ever to find those genes. And the search is paying off.
We were never able to even, imagine 5 years ago that we would be able to do the kinds of studies we've been doing today.
It all began with one family that wouldn't take no for an answer. The family of a small boy named Dov Shestak.
When Dov was a baby, he seemed pretty normal. He was making eye contact, he was laughing, he was babbling. He would try to get our attention as we walked by, and all the regular little baby things.
But when Dov was about a year old, he stopped responding to his name, stopped making eye contact, and finally, he stopped talking. His parents, John and Portia, were told that Dove had autism and was probably severely retarded. There seemed little hope he would ever get better.
I couldn't accept the idea of this death sentence on my very young child.
Portia took it upon herself to learn all she could about autism. She studied all sorts of literature on the brain and started contacting scientists, literally hunting them down. She went to one of the biggest brain science meetings in the world, held by the Society for Neuroscience, which draws more than 25,000 researchers. Among them, a geneticist from Boston named Rudy Tanzi.
To be quite honest, when I was first contacted by John and Portia, I didn't know anything about autism.
But early in his career, Tanzi discovered the first genes that cause another complicated brain disease.
Alzheimer's, we never
Alzheimer's. He did it by analyzing hundreds of DNA samples from families with Alzheimer's victims. Intrigued by autism's mysterious genetic links, he gave Portia and John a critical piece of advice.
I told him that if you want to find genes for a disease, the first thing you need is family material. You need families with autism, lots of them, and DNA.
Portia put together a team that traveled all over the country, collecting blood from families with at least 2 autistic children. After a couple of years, she'd built a scientific goldmine. And here it is, Portia's Autism DNA Bank. It may not look like much, but these are samples from 1,000 families, now tucked away in this rather nondescript looking fridge in Rudy Tanzi's lab. As the search for genes began, there was another puzzling clue about autism. Children don't seem to be born with it. For the first year or so, their brains appear to be developing normally.
Most of our brain is formed beautifully by gene programs early in the fetus. And this gives us a brain structure that is similar from one person to the next. The right parts of the brain are wired up appropriately.
The symptoms of autism often don't kick in until after the first year of life, as millions of brain cells called neurons connect with each other by sending chemical and electrical signals throughout the brain. For normal brain function, these signals have to be sent at exactly the right place and time.
One principle of brain development is timing is everything. Whereas in real estate, it's location, location, location. In the brain, it's when things happen.
Since genes control much of brain development, it's possible faulty genes might disrupt the process in autistic children. And those faulty genes might well be hidden somewhere in the new DNA bank.
So this is where it all happens, huh?
This is where it happens.
To find them, Tanzi collaborated with Mark Daly and colleagues at the Broad Institute in Boston, who've developed cutting-edge DNA screening programs.
This right here is a gene chip,
okay,
which performs the ultra-high-resolution DNA fingerprint of each individual.
So you take our family, our genetic samples from our autistic families, and you load them onto this chip.
Each one of these gene chips contains DNA from an autism family and DNA from a family that's disease-free. Scanners read the DNA sequences, the A's, C's, G's, and T's that make up our genes, and compare them. Millions of these chemical bases across the entire human genome can be analyzed in a matter of hours. Any difference between the normal DNA and DNA from the autism bank could be an important clue.
And for the most part, you're interested in where there isn't a match.
Well, in many cases, that's one of the first things that we look for.
One place the scientists found a mismatch is on chromosome 16. The dip in this red line reveals a section of the chromosome where a big chunk of DNA with at least 25 genes is missing in some of the autism families. This deletion is rare, but vicious. It increases the risk of autism 100-fold. That may be because some of the missing genes are critical players in wiring the brain. If these genes are broken, then perhaps the circuitry of the brain is broken as well.
You may end up with situations in which you have too much information being transferred, not enough information being transferred. Something may not be working in the critical first period of life when so much is being learned and so much is developing and changing in the brain.
The team's next discovery was even more interesting.
On chromosome number 5, they found a stretch of DNA that's present in all of us, but is altered in some of the autism families.
This particular genetic marker.
In the middle of this DNA is a mysterious gene with no known purpose. But its location is a tantalizing hint. It's right next door to a gene called SEMA5A.
We look it up, and we see this gene's involved with how nerve cells connect with each other in building your neural circuitry of the brain during development.
The fact that SEMA5A is so close to the mystery gene is intriguing. Genes in the same neighborhood can have similar functions.
Basically,
it's possible that one or both genes could be involved in autism. And significantly, the altered stretch of DNA showed up in almost 10% of the autism families. That's a large enough number to suggest it could play a real role in the disease, and an important step toward understanding autism.
When you know that there's a gene with a defect, you can think two different ways about it. One is that, was the brain not wired correctly in the beginning? And that's the worst case scenario, because it's tougher to fix a circuit that's not built right. But these kids function. They can still love, they can still learn. So there's still a lot of optimism that maybe we can go in, and if we figure out what's wrong with the neural circuitry, we can figure out a way to make it work better. So at least improve the lives of these kids. And, you know, if we're really lucky, maybe even exclude most of the disease symptoms. But it's genes that are teaching us how to do that.
Dov Shestak is a remarkable example of how the brain can still function, even with severe autism. Dov had never learned to talk, but when he was 9, he was able to start communicating by pointing to letters on an alphabet board.
A galaxy is okay.
He was asked for what a galaxy is,
G?
and to everyone's amazement, he pointed to the letters that spelled out a group of stars.
O U E group.
He knew how to spell, he knew how to read. He had normal intelligence, which we never could be sure of. One of the first things we asked Dov when he began to communicate was, "What have you been doing all these years?" And he just typed out the word listening.
Dov is 17 now. He'll always live with symptoms that make it hard for him to function. But even as he struggles, he goes every week to a bar mitzvah class for autistic children. It's a rite of passage no one ever thought he'd experience. For Dov, his family, and everyone else affected by autism, it's a source of hope.
Hope's a very good thing to have. I think you kind of can't live without it. I think that had we not hung on to it then, whether or not people called it false hope or not, we wouldn't be where we are now. So I think hope is a very good thing.
Who did the painting? Who did the painting? Who did the painting?
And now for some final thoughts on the search for planets. For the longest while, we just assumed that other star systems in the galaxy would look just like ours. A few small rocky planets near the host star, some larger gas-rich ones farther away, and perhaps a swarm of comets and asteroids to round out the family. Turns out, none of the nearly 300 star systems in our catalogs looks anything like ours. Most have giant gas planets orbiting relatively close to their host star, which would gravitationally disrupt any smaller rocky ones nearby. Of course, the search methods today are more likely to find these kinds of star systems, so we shouldn't jump to conclusions. Just as your lost car keys could be anywhere in the street, but you're more likely to find them under the lamppost, since that's where the most light is. The search continues for rocky planets at the right Goldilocks distance from their host star, where water remains in its liquid phase. We care about them because we're driven by the search for life as we know it, and by the prospect of finding life as intelligent as we are. But what about the search for life as we don't know it? Just because Earth is good for us, and just because we call ourselves intelligent, doesn't require that alien life prefers rocky planets, or would even judge us to be as intelligent relative to themselves. Just a call for an open mind on the frontier of cosmic discovery. And that is the Cosmic Perspective. And now, we'd like to hear your perspective on this episode of Nova Science Now. Log on to our website and tell us what you think. You can watch any of these stories again, download additional audio and video, explore interactives, hear from experts, and much more. Find us at pbs.org. That's our show. We'll see you next time.
This Nova program is available on DVD. To order, visit shoppbs.org or call us at 1-800-PLAY-PBS.